Okay, can I have everyone's attention, please? I want to make a few announcements before we begin, and the first is to remind you that you have a midterm coming up on Wednesday, all right? And you already know that I've assigned seats for each one of you. And so please take the time to go to the class website and find your seat assignment. The exam is for 45 minutes, and so it is very, very important that I start the exam promptly on time, because otherwise it's going to come out of your time. And so it's important that you look at the class. There is a chart of the class seating, and I want to remind everybody that if your seat assignment is between 100 and above, it's the center aisle. If it is between 0 and 99, and it's an odd number, it's on this side. No, I'm sorry. An even number is on this side, and the odd number is on this side. All right? So when you come in, it's important that you find your seat as soon as possible. Okay? If somebody is in your seat, it does not mean that you find another seat. It means that you need to let me know, because somebody has made a mistake and has taken the wrong seat. And it's important for me to make sure that you are in your correct seat. And the reason for this is there are multiple versions of the exam, and each of your student ID is linked to a certain exam. And so if you're seated in the wrong seat, it means you took the wrong exam, and that would be considered cheating. All right? You have to be seated in your assigned seat. Okay? So please, we need to do this expeditiously, and so I need you guys to check ahead of time, come a few minutes early so that you find your seat, because as I always tell you, on the exact hour I will start passing the exams out. So if you can come a minute before and find your seat, that would be great. If you come late, I'm going to ask you to stay outside, and I'll start the exams and then let you in, okay? Because I need to make sure for those students who come on time that they have all the possible time to take the exam. Is that clear to everybody? Now lastly, as far as the content on the exam, it will cover everything that we do right up to today. All right? And if you notice, I assigned a last-minute homework that's due tomorrow on buffers. And usually I don't do that. I don't want to assign a homework just before your exam, but I have no option, because I do want you to take a look at those problems before you take the exam, because buffers will be on the exam as well. However, what I'm going to be doing is, even though I make the due date for that homework due on Tuesday, I just want you to take a look at it, and if you don't score 75% or more, that's okay, because I'll give you leeway. After the exam, you can go in on Thursday or Friday, and if you want to get the best score on that homework, you can just get another homework, all right? But I do want you to take a look at this homework. So even though the due date for the homework is tomorrow evening, you have some grace period to complete that homework after the exam, but I think you should take a look at those problems, because they will help you prepare for the exam, okay? So before I begin on the material for today, does anybody have any questions? Great. So the last thing I want to mention is that this class is completely full, and therefore if you are a left-handed person, you may have been assigned a right-handed seat, and if you are a right-handed person, you may have been assigned to a left-handed seat. And the reason is that I have no choice, because every seat in this room is taken, and so I'm just randomly assigning seats, and I'm going to say that, you know, grow up and live with it, okay? However, if it is going to be extenuating, if you find that it's going to really affect your performance, then raise your hand during the exam. After you've got your student ID coded exam, I'll be happy to move you to somewhere else. Okay? There are seats in the front, and I can move you up front, but if it's really going to bother you, let me know on the day of the exam. Okay? Anything else? Okay, so if you guys remember, last class we looked at buffers. And one of the things that you should be able to do is to identify a buffer. So if you're going to identify a buffer, you need to know what characterizes a buffer. And we said the first important thing is a buffer has a weak acid and a weak base that are conjugate to one another. So you have to have a weak acid, weak base, and they are conjugate to one another. And we looked at several examples. One of the examples that we looked at was if the weak acid is acetic acid, then its conjugate base is acetate anion, but acetate anion comes as a salt. So you look at the sodium salt or the potassium salt of sodium acetate. Okay, so in this case, it would be, in reality, what you have is the weak acid and its conjugate base. Okay? If you have something like formic acid and you have the salt of that, and in reality what you have is the weak acid and its conjugate base. Or if you have something like ammonium chloride, which is the conjugate acid of a weak base, then you would have NH3. In reality, what you have is NH4 plus and NH3, and they're conjugate to one another. Okay? Now you'll also see other examples like if I take NH4 plus and replace one of the hydrogens with methyl group so that I have a CH3. So if you have CH3, NH3Cl, can you see the difference between these two is one of the hydrogens have been replaced by CH3. All right? So if you have this and CH3NH2, this would also be a buffer, and this is the acid form, and this is the conjugate base of that acid. And so if you want to look at the combination, this would be CH3NH3 plus and CH3NH2. All right, so if you see something that you haven't seen before, just kind of look at it and see that that's very similar to NH4 plus. The only difference between the two is that one of the hydrogens in NH4 plus has been replaced by CH3. Okay? So these are all examples of a buffer because you have both. You have to have a mixture of both if it's going to act as a buffer. If you just have the weak acid, if you just have the salt alone, it's not a buffer. Okay? The second thing is that we said they must be in approximately equal amounts. All right? They don't have to be exactly the same concentrations, but they have to be of the right order of magnitude. All right? And they should be in approximately equal amounts. And three, the best buffers are the ones that have them in substantial amounts. So the third is in substantial amounts. And when we say substantial amounts, we mean higher concentrations. All right? And if these three criteria are met, then you know that it's a buffer. All right? And last time we said the way a buffer works is that you have both the weak acid. So let's look at it in terms of the generic terms. You have a weak acid in equilibrium to give you hydronium ion aqueous plus A minus aqueous. And remember, the fact that it is a buffer is because you have substantial amounts of this and substantial amounts of that. So what do we mean by substantial amounts? So one molar, for example, is considered a substantial amount. Okay, so if you take 1 molar concentration of each, they're in equal amounts, and that would be a good buffer. So now you ask yourself, how does this act as a buffer? It acts as a buffer because if you add acid, so if you add H3O plus by adding a strong acid, now what happens is your hydronium ion concentration has gone up, so the added acid will react with A minus. So you have H3O plus reacting with A minus, to give you HA plus H2O. So added acid is consumed by this reaction because you have substantial amounts of A minus as well. The conjugate base is in large amounts and therefore can absorb the added acid, and therefore in that way the added acid is consumed and therefore the pH does not change all that much. If you add a base, so if you add an acid, it reacts with this. If you add a base, it reacts with that. Remember, you have substantial amounts of HA. So if you add hydroxide ion, now what happens is the weak acid part of it will react with OH minus to give you H2O plus A minus. All right? So this is how a buffer acts. Because you have substantial amounts of both components, one component will act to absorb any added acid and react with it. The other will function to react with the hydroxide and consume any added hydroxide. And the net result is that the pH is not altered very much. So we took an example last time where we looked at a problem. And if you remember, we started by saying that you started with 1 molar of the weak acid, 1 molar of the weak acid and 0.5 molar of the salt. And we said we would set up this equilibrium. So we would set up this equilibrium where at the beginning you'd have 1 molar of this, 0.5 molar of that, and then you would solve this in a manner in which you'd solve any other equilibrium problem. All right? We know which direction it's going to react. Since there is no hydronium ion here, it's going to proceed in the forward direction, and therefore we know that this will take place in that direction. Therefore you have minus x plus x plus x. You set up the equation, solve for it, and then you can figure out what the pH of that solution is. And we said the pH comes out to be 3.451. Okay? So this is the pH of that buffer. Now we said in the second part of that problem, we said what happens if you add 0.1 molar of a strong acid to this buffer. So now we took this buffer and we added 0.1 molar solution of HCl. Now I want you to look at this. You have 0.1 mole HCl in 1 liter of the buffer. Let's say the solution is not in the buffer, but let's say we place this in pure water. So if I have 0.1 moles in 1 liter of pure water, what would the concentration of hydronium ion come out to be? 0.1. Can everybody see? Because hydrochloric acid is a strong acid, therefore it's going to dissociate completely, and therefore it's going to give you a 0.1 molar solution of hydronium ion. What is the pH of 0.1? 0.1 is what? 10 to the negative 1. So what is the pH of that solution? 1. So if I take this amount of HCl and put it in pure water, the pH will change from pH 7 to pH 1. Can everybody see that? So that's a big difference. It's 6 orders of magnitude. It's going from pH 7 to pH 1. So that gives you an idea that we're actually adding a lot of hydronium ion. All right? However, if we take this amount of hydronium ion that when we place in water brings about this dramatic change in pH, if we place it in this buffer, we calculated what the new pH should be. And remember, if you take hydronium ion, added hydronium ion would react with its conjugate base to give you the weak acid in water. So you would treat it like a limiting reagent problem where all of the hydronium ion is consumed. And now you treat it like a new initial. Once hydronium ion is completely consumed, this is your new initial, and then we're going to calculate the pH of this solution. So we started with 0.5 mole concentration of the salt, conjugate base. It's going to react with the hydronium ion. And so at the end, you're going to have this as the limiting reactant. This will react with 0.5 to give me 0.4 of that. And over here, as the reaction proceeds this way, the amount of product would be 1.10. So now, once I add the hydronium ion, and my acid concentration and my conjugate base concentrations have changed, and this is my new initial, I'm going to calculate the pH of this solution. And so then I would set about doing this the same way that we'd solve any other equilibrium problem. So our new initial would be now 1.10 molar of the weak acid and 0.40 of the conjugate base. And if you solve for it, it comes out to be pH about 3.31. All right? Now I want you to compare this pH with the pH of the buffer that we started with. So here, this is the pH of the buffer to begin with. This is the pH after you add the acid. Now the pH has changed to 3.31. So you can see that the change is only small. It goes from 3.45 to about 3.31. So that change in pH is not a big change. But remember, if the buffer was not there, and if you had pure water, it would have changed from pH 7 to pH 1. So you can see the amount, we added a tremendous amount of hydronium ion, and regardless of adding that much of hydronium ion, you can see that the pH only changed by a very small amount. And that's how buffers work. They're able to withstand added acid or added base, and the pH only changes very slightly. And to put things in perspective, you will see that that same amount of hydronium ion will bring about 6 orders of magnitude in change in pH if it were just placed in pure water. Okay? Now, it turns out that I want to show you, once you identify that it's a buffer, you don't have to go through sort of this lengthwise process of solving the problem. There's a shorter way to calculate the pH of a buffer, and I'm going to show you how to calculate the pH of a buffer that's much easier. And let's take a generic example. So let's say that I have a weak acid in water giving me H3O plus aqueous plus A minus aqueous, and let's say that's the Ka of that acid. And we know what makes this a buffer if you have substantial amounts of Ha and substantial amounts of A minus. So you have to have both of those. And let's say I have 1 molar of that and 1 molar of that. Okay? To begin, we said we're not interested in the concentration of water. You have 0 of that, and therefore we know that's going to proceed in the forward direction. Therefore, this would be minus x plus x plus x. So this would be the initial concentrations. This would be the change. And at equilibrium, we know the concentration would be 1 minus x. This would be x. This would be 1 plus x. And we said because these are all weak acids and their conjugate bases, we know that x is going to be really small. In all of these instances, we approximated them to be equal to the initial concentration. All right? If x is really small, then we can make this approximation. And what that means is, that means this is equal to the initial concentration that you started with, and this would be the initial concentration of A minus. So in all these problems, because they react only to a very small extent, we know that that amount of change is going to be really, really small. And so we can say that the initial concentrations don't change very much. All right? And therefore, I can set up the equilibrium expression, and I know Ka equals hydronium ion concentration times A minus concentration divided by Ha. And if we make that approximation, we can say this is approximately equal to hydronium ion concentration times the initial concentration of A minus and the initial concentration of HA, the weak acid, and its conjugate base. Now remember, in all these buffer problems, we are interested in looking at pH. All right? And pH depends on hydronium ion concentration. So if I take the hydronium ion concentration onto one side and take the other terms to the other side, we looked at this last time, and we said that the hydronium ion concentration really depends on this ratio between the weak acid and its conjugate base. All right? And therefore, this is hydronium ion concentration. And I'm interested in looking at pH, so how do I convert hydronium ion concentrations to pH? Take the negative log. So if I take the negative log of the hydronium ion concentration, and if I do any operation on this side, I need to do the same operation on the other side as well. So this would be negative log Ka. Now I'm going through the log scale, so this is a multiple. So in a log scale, as all of you know, that becomes a plus, okay? And I'm going to take the negative log of the ratio of the initial concentration of the acid to the base. All right? So now I know negative log hydronium ion turns out to be pH. Negative log Ka would be pKa. This will give me negative log acid over the conjugate base. So the ratio of the initial concentrations of acid to base. All right? And this equation is very, very useful because once you know it's a buffer, then all you have to do is, if you want to figure out the pH of a buffer, you just look at the pK of the acid minus the log of the ratio of the acid to base. All right? Now, if you look at your textbook, this form of the equation can be written like this, or it can also be written like this. pH equals pKa plus, if I take the inverse of that, this sign becomes a plus. So it's log base over acid. All right? So just stick to one of these. And I'm going to be always using this equation. And these equations are called the Henderson-Hasselbalch equation. And this is the easiest way to calculate the pH of a buffer. All right? So let's go back to that problem that we calculated before. Remember, we can do the same thing. So just remember this, and you don't have to go through the whole process of setting up the equilibrium expression. So if we want to apply that equation to this example that we've looked at before, you're told that you have 1 mole of HCOOH and 0.5 moles of HCONO added to the water and diluted to 1 liter. So we know that the initial concentration of formic acid is 1 molar. We know that the initial concentration of the formate anion, because that's a salt, it's going to dissociate completely. We know that its concentration is going to be 0.5 moles divided by 1 liter, which is 0.5 molar. They tell us that Ka is 1.77 times 10 to the negative 4 molar. Therefore, we know that if you take the pKa of the solution, that pKa comes out to be 3.752. All right? This is a 3 sig fig number. Therefore, your pKa will go to 3 decimals. Okay? So now, I have everything that I need to figure out the pH of the solution. The pH would be pKa minus log the concentration of the acid form divided by the concentration of its conjugate base, which is 3.752 minus log the acid form would be 1 molar divided by 0.5 molar. So that's 2. So you take the log 2, and therefore that comes out to be 3.752 minus 0.301, which gives me a pH of 3.451. So this was the pH of this buffer solution that we calculated before, but now you can see it's a lot faster. All right, once you identify it as a buffer, now you can quickly calculate what the pH of that solution is. Now, if you take the second part, we know that we've added hydronium ion. All right? And so for the second part, you have to first look at the new initial. So we know the added hydronium ion would react with what? The conjugate base or the acid? It's going to react with the conjugate base. And so what you do is you quickly set up a limiting reagent setup where we know that the conjugate base will react with the hydronium ion to give you formic acid plus H2O. So we know that before reaction, you have the formate ion would be 0.500 molar. You have, we calculated this to be 0.10 molar, and this is 1 molar. And therefore, after reaction, this would be 0.40 molar. This is the limiting reactant. You're going to end up with 1.10 molar of that. Okay? Therefore, I can say pH equals pKa minus log the concentration of the acid over the concentration of the conjugate base. This is now my new initial. So this would be 3.752 minus log of the acid form would be 1.10 molar divided by 0.40 molar. All right? And this will come out to 3.752 minus 0.439, which will give me 3.313. All right? And so once again, this gives me the pH of that new solution. And therefore, this is a much quicker and easier way to figure out what the pH of the solution would turn out to be. All right? So we've looked at buffers, and now you have an easy way to figure out the pH of a buffer. All right? And you should use this. So on the exam, if you see a problem and you identify that it's a buffer, you don't have to go through working out the entire equilibrium process. You can just use this equation and figure it out. Okay? So now we're going to move on to looking at something that's very applicable in the laboratory, and that is designing a buffer. All right? So we're going to look at designing buffers at specific pH values. Now, if you are, all of you recognize that buffers are very, very important, all right? If in the laboratory, if you're a chemist, and if you're in the laboratory and you want to study a reaction that's very, very sensitive to changes in hydronium ion or changes in hydroxide ion concentrations, then you carry out that reaction in a buffer. If you're a bio major, you know that very often if you're going to be studying cells or biological systems that are very, very sensitive to changes in hydronium ion or hydroxide ion concentrations, you study them in buffers, all right? Because it turns out that buffers are very, very important for many biochemical and physiological processes. For example, just take most biochemical transformations are very, very sensitive to pH. An example is your blood. Take your blood, all right? The pH of blood is 7.4. If by some chance the pH drops to below pH 7, or if it's raised about 7.8, so blood is around 7.4. If it drops by 0.4 pH units and goes to pH 7, if it drops below pH 7, or it goes above 7.8, it brings about instantaneous death, all right? And because all these biochemical transformations are very, very sensitive to pH. And it turns out that blood is a buffer. There are carbonates, there are phosphates, there are proteins in the blood that act as a buffer. So you have both the weak base and its conjugate acid in equilibrium with each other, and they act as a buffer to maintain the pH of the blood at 7.4. If you are a student who's going to go on to do, research, very often if you're going to study cells and so on, you actually carry out these studies in buffers. And therefore, you should be able to prepare buffers in the laboratory. And so when we talk about designing buffers at specific pH, this sort of is what you do in the laboratory. How do you go about designing an appropriate buffer for your experiment? Okay? And so let's start by just taking an example where you want to prepare a buffer. So an example is design a buffer at pH equals 4.60. So now your task is that you want to carry out an experiment where you want to maintain the pH at 4.60. All right? So if you're going to make a buffer, remember the relationship that whenever we deal with buffers, the relationship that we want to keep in mind is pH equals pKa minus log of the initial concentration of the acid to the initial concentration of the conjugate base. Now, all of you recognize that if this concentration and this concentration were the same, for example, let's say I had 1 molar of the weak acid and 1 molar of its conjugate base, they would cancel each other and you'd end up with 1 here. The ratio would be 1. What is log 1? 0. So if you have exactly equal amounts of the acid and its conjugate base, you know that the pH should always equal pKa. All right? So if you pick any combination, so if we go to the table of weak acids and their conjugate bases, and if you look at this, remember a buffer has to have a weak acid and a weak conjugate base. So that means that the buffer range would involve these. All right? So any one of these, if you have, this is the acid form, this is the weak acid, this would be its conjugate base. So you know that if you have equal concentrations of both, what do you think the pH of that buffer would come out to be? It's the pKa. So if I wanted, a buffer at 3.75, I know that if I take 1-to-1 ratio of these two, the pH of that solution will be 3.75. If I take acetic acid, you can see that if I take acetic acid and if I have equal amounts of both, then my pH would be 4.75. So remember, a good buffer is one in which you have both of the weak acid and its conjugate base. Second, we want them to be approximately equal concentration. So if they are exactly equal to each other, then you know pH equals pKa. All right? And thirdly, we want substantial amounts. So our desired buffer that we want to design has to be 4.60. And you can see that there's no combination that gives us exactly what we want. We want 4.60, and we don't have any combination that gives us a value that's exactly 4.60. All right? If we wanted to design a buffer of 4.75, then we know we just pick acetic acid and put equal amounts, like 1 molar and 1 molar, and mix them together, and I would have a buffer that's 4.75. So what I do is then I pick the one that has the closest pKa value to my desired pH. So if you look at this, we have a couple of choices. We have 4.19, that's a little far off. All right? We have 4.72, close. And we have 4.75, close. And then if you go to 4.87, now moving too far away. So we actually have two potential choices. We can pick 4.72 or 4.75. Now you want to pick compounds, the weak acid and the weak conjugate base, that are appropriate for your study. Sometimes if you're studying something and your buffer reacts with your reaction, then that's not a very good buffer. If you are studying cells, for example, and you pick a buffer that's toxic for the cells, then your study's out the window because you know, your buffer is actually destroying your cells. All right? And therefore, it's important that you pick the right combination. So between these two, you can see that, let's say for this study, we want to look at tissues. And we want to look at we want to study tissues, and we want to maintain the pH at 4.60. So can you see between these two, acetic acid seems a better choice. Vinegar is more readily available, and we know that it's not going to be, there are not going to be any side reactions and so on. And so between hydrozoic acid and acetic acid, a better choice would be something that's more readily available in the lab. And so acetic acid would be an appropriate choice. Even though we have another one that's closer, we're going to pick acetic acid because that would be more appropriate for the experiment that you're designing. So once you've picked the choice, now what you do is you go back and you say, so we pick, so the first job is to pick the conjugate acid base pair. And so our choice is acetic acid and sodium acetate. And we know for this pair, pKa equals 4.75. So you have to have the list of the combinations of weak acids and their conjugate bases, and you can go through the list to pick out the right choice for your buffer. It turns out there are handbooks available that would list out hundreds and hundreds of different types of buffers that you can use. And so you pick the appropriate one that has the chemical properties that you want, as well as the pH. All right? So once you've chosen the buffer, now you have to figure out how are you going to prepare this buffer so that it'll have a pH of 4.60. So what we know is we know our desired pH is 4.60. So we say pH equals pKa minus log. Now what we're going to look at is acetic acid, so CH3CO2H. That will be the initial concentration of the acetic acid divided by the initial concentration of its conjugate base. The desired pH is 4.60. We know that acetic acid has a pK of 4.75 minus log the concentration of acetic acid to the ratio between the two. So if I rearrange this equation, you can see that log of the ratio of the initial concentration of the acetic acid to its conjugate base should equal 4.75 minus 4.60, which is 0.15. All right? So now if I take the inverse log of that, I can figure out the appropriate ratio of acid to its conjugate base. And if you take the inverse log of that, that comes out to be 1.4. All right? So that means that if I want to prepare a buffer that has a pH at 4.60, now the ratio has to be 1.4, ratio between the acid to its conjugate base. If they were a 1-to-1 ratio, you know that pH would equal pKa. All right? But we don't want a pH of 4.75. We want a pH of 4.60, and therefore our ratio has to come out to be 1.4. So that means that whatever buffer I prepare, it has to have this concentration ratio between the two. All right? So possible choices would be, if I have, let's say, initial concentration and my conjugate base. So if I have, let's say, 2.8 and this would be 2.0 molar. So can everybody see that if I have this ratio, so if I start with an initial concentration of 2.8 molar and 2 molar, that ratio comes out to be 1.4. So if I mix if I take the concentration of the acid and the concentration of the conjugate base and mix them together, that would give me a ratio of 1.4. Or I can say that I want it to be 1.4 molar and 1 molar. That's another possibility. You have many options, all right? Or I can say I want 0.28 molar and 0.20 molar. Or I can go to 0.14 molar and 0.10 molar, all right? Or I can go to 0.014 molar and 0.010 molar. Do you see that all of these ratios of concentrations will always give me a ratio of 1.4, and all of these buffers would give me a pH of 4.60, all right? But if you look at this, remember, one of the properties of the buffer is to be able to withstand added acid and base. And so what happens is that higher the concentration, remember we expect them to be in substantial amounts. So what we say is, as you increase the concentrations, we say that the buffer capacity improves. And what is buffer capacity? The buffer capacity, this is the ability of a buffer to withstand added acids or bases. All right? Without being swamped. So can everybody see that every buffer will have a certain limit? And so if I take this example, let's take this buffer. If I prepare this concentration and this concentration of buffer, all right, it will have a pH of 4.60. But what if I had 1 molar concentration of hydronium ion? Can you see if I add 1 molar concentration of hydronium ion, the hydronium ion concentration is almost 100 times greater than this. Do you think this is going to be able to act as a buffer when you have that much acid added to it? So this buffer has very limited buffer capacity because it will be easily swamped by added acid and base. But if I take 1 molar concentration of hydronium and add it to this, can you see now it's not going to be swamped because now this is in greater amount than the acid that you're adding. So this will have a better buffer capacity, and that's why we say, you know, the 3 criterion for a good buffer is what? That they should both have the weak acid and its conjugate base. They have to be approximately equal amount because the closer they are to each other, the pH equals pKa. All right? They don't have to be exactly the same, because to get the desired pH, you're going to adjust them slightly. All right? But the best ones would be where you have equal amounts of both, and that would be when pH equals pKa. And then the third is substantial amounts. And the reason we want substantial amounts of both is because the more weak acid and conjugate base that we have, the better it's able to withstand added acid and base. In other words, the buffer capacity is better. All right? So we need to meet all of these 3 criterion when we design buffers. All right? So if you are ever asked to design a buffer, you start with the desired pH, and then you go to the list. And there are many, many lists available. And the first step is to find the appropriate conjugate acid-base pair. All right? Once you pick that, then you can figure out what ratio do you need to have both of those. And once you figure out the ratio, then you have to ask yourself, what is the buffer capacity that I want? All right? And if you want really good buffer capacity, then you have to pick ones that have high concentrations of both. Got it? So that kind of finishes up looking at buffers. And then that kind of leads into the next topic that we're going to look at. So as far as the midterm is concerned, you will only have to study up to buffers. Okay, so make sure you review up to buffers. Now we're going to move on to looking at the next topic, the last 5 minutes, which is looking at acid-base titrations. So we're going to look at acid-base titration curves. Now, all of you have seen a titration, haven't you? Can I have a show of hands? Who, if you have seen a titration, raise your hands. Anybody who's seen any titration? Have you guys carried out titrations in the laboratory? Somewhere during this quarter, you will be doing titrations in the lab. This week. Great. So the timing is great. So you're going to do this in the lab. Now, when you do a titration, all of you know that you start with a burette, right? And in the burette, you place the known concentration. So solution with known concentration. And because it's a solution with known concentration, we call it the titrant. All right? And in the Erlenmeyer flask in this flask is the solution with unknown concentration. And what do we call that? We call that the analyte. Okay, so let's start by saying, why do we want to do titrations? Titrations are an analytical tool. It helps us determine the concentration of a solution. All right? And from that, we can calculate the amount of solute that's dissolved in that solution. So in order to do a titration, we have to take into account a reaction that takes place cleanly without any side reactions. So a titration looks at a reaction between the titrant and the analyte, and this reaction has to be a clean reaction without any side reactions taking place. All right? And we take advantage of that reaction to figure out how much analyte you have, to figure out the concentration of your unknown solution. So it's an analytical tool that helps you determine the concentration of an unknown solution. So in order to figure out when the titration is complete, we take advantage of some physical property of that reaction. Sometimes the reactions change color. So when the two reactants have reacted, so your titrant and your analyte have reacted completely, the completion of that reaction has to be signaled in some way. One way you signal the completion is if you have colored reactants and the reactants change color. All right? Another way for you to signal the completion of that reaction is to use an indicator. So you add a third reagent in there, and that third reagent changes color. All right? Another way, remember, you just have to take advantage of some physical property. Another way of figuring out whether the reaction is complete is to do a pH titration curve. When you look at that, you follow the, especially for acid-base titrations, what you do is you follow the pH. And when the reaction is complete, there's a sudden jump in the pH, and you look for that sudden jump in the pH, and that tells you that the reaction is complete. Okay? So ultimately, titrations are used as an analytical tool to figure out the concentration of the unknown solution. So in any titration, you start by putting the known concentration. So you have one reactant of known concentration, and that goes in the burette. You have the unknown concentration, and that's the one that goes in the flask, and we call that the analyte. Then you have to, for that particular reaction, you have to figure out how am I going to signal when the reaction is complete. And so you can, depending on the reaction, there are different ways. The most common one is to add an indicator. So you add a third reagent that changes color that signals the completion of that reaction. All right? But in this class, because we're looking at pH, and we've studied pH in detail, for us, the physical property that we're going to look at is pH. All right? And so in acid-base titrations, the completion of the reaction is signaled by a sudden jump in pH. All right? And so we examine the pH dependence as titrant is added to the analyte. All right, so what we're looking at is here, the physical property that we're going to look at is the pH of the solution. And so what we will do is we'll monitor the pH of the solution as you add more and more titrant. So a plot of the pH of the solution, all right, in the flask. So a plot of the pH of the solution as a function of the volume of titrant added is called a titration curve. All right, so if we're going to plot the pH as a function of the volume of titrant added, then what we end up with is a titration curve. Okay? So on Friday, we will start looking at acid-base titration curves. All right, so I'll stop there for today, and then we'll start looking at this in greater detail.